aspects of generalizing strong measure zero sets in certain directions, actually. So the talk will consist of several parts, maybe, and mainly contains some, not many results, but rather talking about a few concepts and asking questions to you, actually, so about things I do not know, I would like to know more about. So let's start with the basic definition of strong measure zero set for those who haven't seen it. So let's just say on the real line, set X is strong measure zero. I will just abbreviate it by S and Z, strong measure zero. It's a strengthening of the back measure zero. So this is the definition if for each epsilon n sequence, so think of it as a fast decreasing sequence, these are the interesting ones, there exists a corresponding sequence of intervals such that the length, so for each n in omega, the length of the interval in is at most epsilon n, okay, and the intervals altogether cover the set X. So X is subset of the union of these intervals. So in set theory, it's more interesting actually. It's easier to prove things because things work out combinatorially to switch from R to 2 to the omega. So from now, so let me restate the thing for 2 to the omega. So X in 2 to the omega is strong measure zero if so let's say for each I in omega, so for each sequence of natural numbers going fast increasing sequence to omega, so to speak, there exists a corresponding sequence of basic closures. So let's say Si, I in omega with property to the length of Si is at least Ni, or you could say for each I in omega, the Si is an element of 2 to the Ni, okay? Such that X is covered by the basic closures generated by these finite bit sequences. Okay, so what do we have? So if this is 2 to the omega, we prescribe a sequence of Ni's and 0 and 1 and so on, and then we have to find a sequence of Si's as 0, as 1 and so on, such that the X is covered by these closures above these sequences. Okay? So this is now the definition of strong measure zero in 2 to the omega. And so now in the first part of my talk, I would like to talk about a certain generalization of this now to the direction instead of omega kappa uncountable. So we just had this conference, this little workshop about satellite workshop of the DMV Tagung in Hamburg about the generalized Baire space. So it fits into this context. So the definition I'm going to give now is actually by Halko in his PhD thesis. So just a straightforward generalization of strong measure zero to 2 to the kappa exactly in this way. So let me write it down again. X subset 2 to the kappa. So now we talk about the generalized Cantor space, so to speak. So if we think of wheels now of the kappa length bit sequences. And so countable means like of size, countable corresponds to of size kappa, and uncountable corresponds to of size at least kappa plus and so on. Okay, so X subset 2 to the kappa is strong measure zero, according to the same way. If for each alpha I sequence of length kappa, so all the alpha i's are elements of kappa going to kappa, there exists a corresponding sequence of si's for the generalized basic closures. So si I in kappa, again for each I in kappa, the si is going to be in 2 to the alpha I, such that X is covered by these basic closures. So we would have the same picture, but the height is now instead of omega it's kappa, giving this alpha I sequence, we can find this sequence of SI such that this happens. Okay? So, and now let me write this in a slightly different way. I mean, completely trivial reformulation. So let's say X is strong measure 0 if for each alpha I there exists an SI such that this holds, such that this is true. Okay? And now this, of course, means nothing else than rewriting this part for each X in X, a set of I in kappa such that this little x is in Si. This is non-empty, right? This is just what it says. This is completely trivial. Now I can make, I can come up with variants of this. I can say instead of not empty, I can say that this set is of size kappa, for example. But this actually turns out to be the same. This is very trivial actually, but still to understand the problem which is going to come in the next variant of the definition, let me briefly sketch this trivial proof. So if this is kappa, so just split kappa into kappa many kappa-sized sets. Okay, so these are the sets A0, A1, and so on. J less than kappa, say. And so of course this seems to be the stronger statement. We want to show that it's the same. So assume we have a set X satisfying this. So usual strong measure 0. We want to show that it satisfies this. What we do? We just given this alpha I sequence, we just use for the alpha i's with the index in A0, we use the fact that X is that it's possible to find SI such that X is covered by this basic global, so it's I in A0. Okay? So this is possible, and now we do the same for A1 and so on for all these, and therefore since each little X is now at least once hit here within A0, at least once within A1, A2, and so on, we in total get kappa many, it's hit kappa many times, and so we get this. Okay? So this is very trivial, but I just wanted to emphasize because now comes the next variant of the definition, and now it's not that clear anymore what we can do. So, what about saying that this set is not of size kappa, but stationary? Okay, this is demanding even more. Okay,
so you assume that kappa is regular, at least not of covenant.
Yes. So I'm not sure what exactly I would like to have, but let's say kappa is regular. So, but in particular, I allow kappa successor uncountable or kappa inaccessible measurable. So I'm interested in both cases. So, okay, and now, so this is the definition. Actually, maybe if I have time, which I probably don't have, I can tell you why I came up with the definition, but then I found out that long time before, Heiko also came up with this definition. It's the exact same definition, but I was interested actually on kappa inaccessible measurable for some reason, and he looked at kappa equals omega 1. So anyway, so this definition now is also due to Heiko, and it just says that we say that X into the kappa is stationary strong measure zero if this holds. So if for all x and x okay. So yes, and so now first of all, let me mention that it's completely trivial, of course, that each, so like counter in the usual case, each kappa-sized subset of 2 to the kappa is strong measure zero in the usual sense. It's clear, you can just cover these kappa many points by the respective SIs. So it's quite easy to see the same for stationary strong measure zero. What you actually have to do is so for any kappa regular uncountable, say, use, so what I want to argue is that the kappa-sized subsets, so this collection is contained so that each kappa-sized subset of 2 to the kappa is actually stationary strong measure zero. Okay. So why is that? Just use Soloway theorem. In the fact that we can partition kappa into kappa many stationary sets. And now do the obvious thing. If you have a set X of size kappa, just and given an alpha I sequence, so just from the indices in A0 in the first stationary set, cover the first point in your kappa-sized set, and with these indices cover the second point, and so on. Okay, just restrict your second generalized real, so to speak, to the respective length of the given alpha i's with I in A1, say, and so on. Right? So this proves this inclusion. So it's also quite basic. So it's somehow in some sense, sensible notion because at least the kappa-sized sets are in there. And as we said, it's a strengthening of strong measure zero, which is either by this or by this definition. Okay. So this is very clear. And now the question is what more things do we know about this? So I do not know much actually, and so yes, why I sketched to prove that these two formulations are the same by this is just to point out actually that one might think that we can now use this partition into kappa many stationary sets to actually prove that whenever we are strong measure zero, then we are always stationary strong measure zero. But this is not true because here we somehow used, we didn't use somehow that the individual elements of the partition are of size kappa, but what we actually used for the argument that from this follows this, we used that if we pick one from each, okay, then the resulting set is still of size kappa. This is what we used, right? And so if we start with the partition of kappa into the stationary sets A, J, and we do the same argument as here, so let the set X, because it's strong measure zero, be covered here with SIs of the lengths with indices in A0 and so on, then we can pick here one point in the stationary set, another point in the second stationary set, and so on. But this resulting set is of size kappa, but in general not necessarily stationary. So this is the problem. So in fact, I thought this is trivial in this way, but it's not at all. And so the question is more or less, this question would more or less end the first part, the first way of generalizing. So what more do we know? So for example, is it, so for any kappa, so kappa regular, is it possible to construct only a very mild question, so to speak, is it possible to construct a kappa plus sized stationary strong zero set? Okay, so and what I mean is under any assumption. We do not know an argument, so to speak, why this notion is not completely trivial in the sense that this here is equal all the time. Instead of C for all kappa uncountable regulars. So under any assumption. So I should mention that for, I didn't say, I guess, that for strong zero, it's as in the case omega, under CH you can construct, under CH you can refute, so to speak, Borel conjecture. This is under CH you can construct an uncountable strong measure zero set, and so here in general also under GCH at kappa, so to the kappa equals kappa plus, you can construct a kappa plus sized strong measure zero set. So this collection is not trivial. So, and yes, so maybe I have 2 minutes to mention why I got interested in stationary strong measure zero sets, because together with Cy Friedman, we discussed the question whether one can obtain kind of general Borel conjectures. Borel conjecture, as I said, means there are no kappa plus sized strong measure zero sets. And so what Halko and Schallach proved is that for kappa successor, this generalized Borel conjecture is always false. So you can, so if you have a kappa successor, you can always find the kappa plus sized strong measure zero set. Okay, and under and for kappa inaccessible, so this seems to be open. So we looked at the question whether one can force, like mimicking the usual labor proof to get Borel conjecture to get a model where there are no kappa plus size strong measure zero sets. And for some reason, it turned out that it might be easier to look at this question first. This approach maybe only yields a model where there is no kappa plus sized stationary strong measure zero set. Therefore, I was interested in whether at all the opposite is possible, namely there are kappa plus sized stationary strong measure zero sets. Okay, so okay, in this direction concerning such proof, I just very separately wanted to ask whether any of you know about, say, labor forcing, generalized labor forcing on kappa measurable. So what I mean is that you have a stem, and then from then on we have always splitting, and splitting in the sense that the set of successors is measure 1, in the sense of the fixed normal measure on kappa. Okay. So yes, and so the question is, does this forcing has a pure decision property? The pure decision property, so that you can decide actually.
What's the size of the tree?
The size, so the height.
The height of the tree is kappa.
The height of the tree is kappa. Yes. So the split. So we have stem of length less than kappa, and here we have the ordinals here are in the measure. And from then on, so like in labor forcing, not in Miller forcing. In labor forcing, we are splitting all the time. And so, because this is less than kappa complete, we have less than kappa closure, and so yeah, so pure decision property would actually mean that you can decide somehow between less than kappa many options, and therefore you could prove like labor property, generalized labor property on kappa. So this would be along these lines. So just, I mean, just to mention, if we replace here, instead of measure one here club, then it's quite easy to show that this forcing would add the Cohen wheel by co-stationary stationary argument, and therefore it does not have the labor property, and therefore it does not have pure decision property. But it's not clear to me at least what happens if we have measure one here, because we do not have like stationary co-stationary to get any Cohen wheel argument here. Okay, so this finishes kind of the first part.
Is that question known for other three forcings?
Sorry?
Is that question known? Is the answer to the question known for other three forcings?
On kappa, you mean?
Yeah, on kappa.
Yeah. So, yeah, for Milam, I mean, I really haven't thought too much about all these things, but I guess for Miller forcing it should be possible. And for Miller forcing it's...
Seems you repeat your proof.
Sorry?
You repeat the proof for choosing on omega, it seems.
Yes, I mean, yes, the problem, I guess, is so for Miller forcing you always have more freedom, so to speak, because you can just make new stems here, so to speak. So the usual proof that labor property, or the pure decision property, and therefore labor property holds for labor forcing omega, is some good node, bad node argument, kind of, but this argument seems to break at level omega, so you cannot pass the limit. So this is the problem. In Miller forcing also in omega, you do not need this kind of complicated argument.
Yeah, one step.
Right?
The Miller forcing one step.
Well, one step is sufficient, right?
Yeah.
Yes. Yeah, you just have two infinite sets, so if you feel not feel, you shrink here and you can allow for more steps, right? And then do it together. So and for labor forcing, you have to do more complicated stuff, and this breaks it. But maybe it doesn't, if you do it in whichever way, I don't know. Actually, Martin Walsh and me thought we have a counterexample so that we are sure that this forcing cannot have the pure decision property, but now also this counterexample.
So you want to decide, you can't decide questions by stem preserving conditions for that labor forcing or kappa. So what is it you want to try to prove?
So you mean you cannot...
It gives you, I mean, you have the axiom of choice, right? So if it has a stem, you could look at the next splitting point. I mean, the next cove omega. Feels like it's showing that every subset of kappa to the omega has to contain a kind of perfect, too much of a perfect set.
This is actually what we tried to do as a counterexample, but it's not clear to us anymore because, I mean, so we could, so usually you can take on omega, so like on omega to the omega, so you can take a non-labor measurable set, so which, yeah, and this, but this you do with the counting argument, so to speak. I mean, you diagonalize against all labor trees, but here are too many labor trees, I guess. So even the cuts below omega, so like kappa to the omega, you have more than you have reals. So maybe I can ask you again later if you have any ideas. Thanks a lot. So, yes, the second part, so to speak, will be very short and even much more tentative. So I haven't thought about the question too much. I'm not even sure whether this is a good question, but let me put the question, maybe you know immediately whether it's trivially true or false or something. So the question is, are there, so on omega 1, I mean, if you want, I can also tell you later on maybe why I'm interested in this question. But are there functions f and g, namely in the following way. So f is a function from omega 1 to 2 to the omega, injective, I guess. So maybe I would like to assume CH, but I'm not even sure about that. So f is of this kind, g is of this kind, the opposite way, 2 to the omega to the omega 1. The omega 1, anything, are there f and g of this kind, such that for any, like t, like translation units in 2 to the omega, this side, from some point on something happens, so there exists an alpha in omega 1, such that for each beta at least alpha in omega 1, the following holds. F of beta, so for all these from alpha on ordinals, so f of beta, we now have a real, right? We add t, so this is, I will in the next part, I will also use this a lot, so this is just the plus on 2 to the omega bitwise modulo 2. Okay, so f of beta is a real 2 to the omega plus t. So this is now another real, right? Now I can use t to get back an ordinal in omega 1. And this should be much larger, at least larger than beta. So I'm sorry that I put this question so out of context. But I mean, there is some relation. Actually, to put it in a bit more of context, I will.
You want something about t, trivially. What about if t is all zeros?
I want to have these two fixed functions f and g, such that whatever t is, I can find the alpha.
Is g injective?
So I guess I do not care.
Some sort of diamond.
I'm not sure whether some structure omega 1, like, I mean, like some folio argument or something rules the question that it's always false. So the thing is, I mean, so I have used a similar thing on for the Beer-Strecker group set to the omega to prove the Gall-Michelsky-Sorey theorem is false there, but anyway, what I used there is actually, if I extract the thing that I compare like omega with something which is a group structure, what I also do here, so under CH of same cardinality, right? So this is with the group structure, this is the ordered thing. For omega or z, I would have the corresponding question, so f is from omega to z, the group structure, the usual, and g is from z to omega, such that for each z in z, okay, this is this side, there is a natural number, such that from this point on, for all natural numbers, the same holds. So f of k plus z, f of k is now in the group, plus z, g of this is bigger than k. So this is, of course, possible.
Read it. Are you saying you're assuming CH and you're asking whether they're F and G?
Yes. I'm not sure whether I want to assume CH, but let's say, yeah.
That's a sigma 2-1 statement, so it's going to be absolute with large cardinals, so presumably one can answer.
Okay.
Right? It can't depend on forcing, but it's clearly sigma 2-1, right? Because you're saying there is a set of reals, F and G, and then it's all local quantified.
So this means it should be, so what does it mean?
There is an answer to your question.
Well, I guess it has an answer. I don't know what the answer is.
Okay. So actually, I would appreciate a positive answer because then I can kind of make the analogous proof which uses this between Z and omega. Also to prove that like generalized dimensions is always theorem on 2 to the omega 1 is well kind of this which I proved for Z to the omega because the non-compactness here that splits like the group splits here to all of this and will correspond to that on height omega 1 2 to the omega 1 you can like interpret this an omega section here as where this functions as something in omega 1 and so now I put it a bit into context. So as I said, this is of course if I put it in the right way, trivially true. Just take F, the identity, and take G like 2 times absolute value. It's only necessary on the positive values. So when Z is very large, you can take this case only for very large, and this is then it shifts just a bit, and so the G doubling it is still bigger than K. So it's easy. Okay, so I guess this second thing I do not have more to say. We know that there's an answer. Yeah, because from now on I will
You don't have, in previous problem, you don't require G to be onto, you don't require to be onto, and not, you don't require to be injective.
no, so
So
I
G
don't
could
think
have
so.
a lot of gaps.
assuming if G is just like fast enough, it's,
Oh, you could even. Okay, let's talk about it later.
so even better, it's like maybe yes, for now I would like to just talk about this on tutoring here again, so forget everything about and so on.
Okay, could you have that G, you just fix any F, could you get this G by forcing? You take any F, and now you try to add this G by forcing, what will go wrong?
So you mean forcing which is even close to something which
Yeah,
isn't?
yeah, so you try to diagonalize those T's and give it time. Probably it's wrong, but okay.
Sorry?
Probably it's wrong, but let's try.
No, very sorry.
Sorry.
Okay, so as I said, for now I would like to stick to tutoring here and go into another direction of generalizing stronger zero set, namely via characterization of stronger zero sets in terms of translation. This is what Galovic-Solvay theorem is about. So, okay, we have the notion for x into the leader of stronger theorem. So maybe I start with the following definition. So if I is an ideal or any collection actually of subsets of 2 to the omega, then we define I star. So this is not very common maybe, but for now I would like to stick to this notation. So this should mean those sets in those sets of reals Y, such that for each set in this collection J, we have that Y plus Z is not the whole set of reals to the media. So I will explain what this means, and the current way of writing it. So as I already said, plus onto the media, we mean the bitwise modular 2 addition. And this should just mean the complex sum, like the set of all little y in y plus little z in z. Okay? So, and you can, case of 2 to the media, everything is very nice because plus and minus is the same, so you don't have to worry too much about equations. So this is the same as saying that there exists a translation wheel such that y translated by t is not disjoint from z. So this means, this is the reason why I call this collection I star, or J star, the collection of J shiftable sets. Okay? So, a set is in J star if you can shift it away, translate it away from any set in J. Okay? So, now we have this motion, and with this motion we can very quickly state Galvin-Michowski's Soloway theorem, I guess from 1976. Says that a set X is stronger than 0 if and only if it is Liga shiftable. So if and only if X is in, if M is the Liga set in M star. This is the main theorem here. Now this gives rise, so here we have some ideal, namely the Liga sets. Now you can replace this ideal by any other collection or any other ideal. So what quickly actually did, guess the fusion by is a set X is strongly Liga. If and only if X is in M star, so if X can be translated away from each Lebesgue measure 0 set. Okay. So this is strongly Liga and connected to strongly Liga, so let's count this. So M Liga ideal and null ideal, so this is M star, this is the strong measure 0 set, and here is M star, this is the strongly Liga set, and connected to this is the Borel conjecture saying that the Liga shiftable sets, so to speak, the strongly 0 sets, are just the countable sets of reals. Here we have the dual Borel conjecture. Which says the same for n star. Okay, that is just the countable sets. So, and what I also considered in my PhD thesis is now to replace this by S0, the Wohofsky ideal. So I would like to talk about the results of this. So S0, let me define what S0 is. And now you can, of course, I'm also interested in not just, so S0 is connected to Sachs forcing, so you can also take any other forcing you like zero forcing or even so let me talk about this a bit later. So first, so X is in a Michowski real, X is in S0. If and only if for each, let me just write in forcing way, so for each Sachs condition, for Sachs tree, there's a stronger Sachs tree such that the body of The stronger one is disjoint from X. Okay, so in other words, without forcing, so whenever you have a perfect set, you can find a perfect subset which is disjoint from X. So this means X in S0. So let me briefly mention why now this is in some sense very different to these cases. Because here, as I already mentioned in the kappa case, and this is of course also true on omega, if you have CH, then you have negation of the Breuer conjecture, so you can construct an uncountable strongly zero set. So the same is true here. You can construct a uncountable null shiftable strongly set. So why is this the case actually? I mean, forget about the elementary definition of strong zero, but let's stick to just Liga shiftable, null shiftable and so on. The basic property of these ideals, which makes it easy to show this under CH, is the fact that these are Borel ideals. So therefore you have a basis of, so a cofinal set in the ideal of size continuum. And then you can do an inductive construction actually to find like uncountable, in general continuum sized sets in the shiftables. We need something like covering of the J. So if this is the J equals cofinality of J, and then you can find a set of this size which is in J star. This is what you can do. And if you have CH and you have a Borel ideal, this is below the continuum, and this is at least RF1 for a sigma ideal, and so therefore under CH this is the same, and it's okay to do that. So in case of S0, you do not have a Borel basis, clearly, but even more is true, you can prove instead of C that the cofinality of the Machevsky ideal is bigger than the continuum. So this, by the way, is, some of you have heard the talk of Yuri Komsky in a joint project with Yuri and Jörg Brendle, where we investigated this very same question for other ideas like LCO connected to labor forcing, where it's also true. This was not known before. But this is not too important for this talk. So, yes, and so because cofinality, even under CH, is above the continuum and covering is less or equal to continuum, you can, about the connection SCO star, it's not clear anymore what is true under CH. Okay, so and here I call this the Machevsky-Borel conjecture, just saying that SCO star is just a countable set. So by this, it could be true that it's just it follows under CH. At least it can be consistent with CH. So
sorry,
yes.
it can be consistent on CH, you mean that it is consistent on CH or you don't know?
No, I now, if you want to know the result is it follows. So this is now what I proved together with Jörg Brendle. It's a very recent result, at least about some version of the proof, which is quite close to the concepts I've already introduced in my PhD thesis. Some of you might know them about with the notion of Sachs lengths and yields. Proof using this, I will sketch the steps now. So, okay, so state that here. So this is that at least I'm not completely sure yet whether this is instead of C or whether it needs the assumption that the continuum is regular. So let's stick for continuum is regular. So I'm sure about that actually, that then if X is of size C, of size continuum, then, so this is in general without assuming CH, then X is not in S0 star. And of course, immediate corollary from that is that CH implies Marchevsky-Borel conjecture, which is the statement that S0 star is just the countable. Okay. But what I will do now is sketch a proof of a bit of a strengthening of the corollary under CH. So it's kind of orthogonal. It uses CH, but we get a bit more than just that S0 star is the countable set. So for that, so what I looked at is, so for now, let's say assume CH all the time, okay? We do not need it all the time, but let's say CH. Okay. So to find out under CH something about S0 star, I introduced the following concept, namely that the collection I is a fact dense zero. This is, by the way, very easy to generalize to other forcing settings. You could also speak about silver denser here and so on. So a sex denser here, I will abbreviate it by SDI with the following holds. If I is a sigma ideal, I is translation invariant, and I is dense in sex forcing. So the sex condition is the stronger one, such that its body is in this collection I. Okay. So yes, this is the concept of sex dense idea. Why I introduced it? Because of the following lemma, this connection to S0 star, CH we have, so that if, yes, this S0 star is a subset of I for any sex dense idea. Okay, so this is the main lemma. In other words, S0 star is the subset of the intersection of all sex dense ideals. Okay.
So this is also assuming CH.
Yes, in particular this lemma is assuming CH. Some of the other things I'm going to say is probably not assuming CH, but let's forget about it. So this, I mean, you have here senior ideal if you would like the general setting where it's not that useful, maybe, I'm not sure. So you would have to say that the additivity is continuum. Okay, this is the lemma. What do we want to prove? I promised you to sketch a proof of this corollary that under CH we have MVC. So we have just the countable sets in S0 star. Okay. So, and I also said I prove a little bit more, and this is what I do. I prove that this collection, the intersection of all sex dense ideals, only contains countable sets. Okay. And therefore, in particular, we have the MVC. So we show the following. So first, so from now on I will concentrate on this intersection and forget about S0 star. Okay, if we want to prove that if you have an uncountable set in there, we will get a contradiction, so to speak. So first of all, I mean, for example, just to see what Sexton's ideals, means, for example, meager sets and null sets are both Sexton's ideals, because translation we are in sigma ideals, and whenever you have a perfect set, you can shrink it to a perfect subset, which is meager null. Okay. So strong measure zero sets, for example, do not form a Sexton's ideal, but you can find many Sexton's ideals such that its intersection only contains strong measure zero sets. So this is so I won't go into details here, but let me just mention that there is a bare space real indexed family of Sexton's ideals such that its intersection contains only strong measure zero sets. So just very briefly in one. So IF says if F is a very fast increasing function, IF says it's a sigma ideal generated by perfect trees which has very few splittings with respect to this fast increasing function. This is what it says. Such a thing is a Sexton's ideal, and then you can quite easily show by the elementary definition, the epsilon definition of strong measure zero, that this is the case. So and then it's also easy to see, and this is what I need for the rest of the argument, that strong measure zero, each strong measure zero set is Marchevsky null itself, so zero itself. Okay. So therefore we know if we have an uncountable set in there, then in particular it's S0. Okay. So and yes, and what the strategy now is the following. So if X is uncountable set in there, we know that it's very small in the sense as zero. So, and I'm more or less about to show that it's even smaller, and because it's so small, we show that it's actually not in there. Because it's so small, we can, it's large in some sense, maybe we find another Sexton's ideal such that it's not in there, and therefore it's not in the intersection. Okay, so that's, and for this we need the following observation, or the following definition. So if a set X is in S0, we would like to find the Sexton's ideal such that X is not in this Sexton's ideal. But this is not quite true, but we have to strengthen the notion of S0. So where I have, yes, this is why I have space here to come up with the strengthening of S0, what I call X in S0 trans. So X is in S0 trans if the same holds true, but also with translation perturbations. So for each sex tree there exists a stronger sex tree, that not just this holds, but okay, sorry. Let me replace this first to make it more obvious. So this is the same, because if you can shrink it away except for countable many points, then you can also, so this is equivalent. Okay. Now let's say for each key into the omega, Q shifted by P is almost disjoint in this sense out of zero many exceptions. Of course, you cannot demand here empty, because at least one point you can always shift into, except for empty set X. This would be another question, not sure. So whether it's the same to say less than equal to 1, or whether there even exist uncountable sets with less than equal to 1 here, so it doesn't matter here. Okay, so, and actually I do not know what about this, if this is the same, or, but I do not care, because of a lemma I will state in 2 minutes. So, but let's first say why this S0 trans is now nice. let x in S0 trans, and the cardinality of x is continue, then there is the sextens ideal I with x not in I. Okay, why is that? Let me prove this it works. This is very easy. This is why I came up with this definition actually. Just constructed by definition this sextens ideal. So what do we do? Look at the definition of sextens ideal. It has to be dense in sex forcing. So fix this set X, and for each sex tree, just take this witness, this cube. And this has the property that all its translates have only countable intersection with the set X. Okay? And because all its translates have only countable intersection, we can also take of these witnesses all its translates and take the sigma ideal generated weight. Okay? And therefore, this sigma ideal generated it will not contain this large set X because of this actually. And we're almost disjoint from X. Okay? And so we know that if X is in S0 trans, it's not in this intersection of all the sextens. So this is what I already had in my PhD thesis, but I couldn't finish the proof of Machevsky-Borel conjecture. But now, with ideas similar to this, the following holds, and this finishing thing, namely that if X is in S0 of size continuum, then there exists a subset X prime of size continuum such that X prime is in S0 trans. I have no time to say anything about the proof, but this is true, as a matter of fact. And now we are finished. Because, so let me just say in words why we are finished. So take X in the intersection of all sextens ideals. Because of this, in particular it's in there, so it's in S0. Okay. Now because it's in S0, by this lemma, we find a subset which is even S0 trans and still large. And therefore, we find this very easy observation. So, because we have now the subset which is in S0 trans, we find another sextens ideal such that the subset X prime is not in there, and therefore the 0% X we started with even more so not in I. Therefore, X in the first place was not in the intersection of all. Yes. This finishes the proof of stage price. And this maybe I do not have much time left, but let me just again as a question for you ask what about what you think is the best way of generalizing things if we are in a context which is not 2 to the meter. So as I said, instead of S0 I can also, I need translations of course for all these arguments because it's about translations. So in 2 to the meter, we use this bitwise model 2 plus. So many of these things also hold for silver forcing. I'm working on this right now. So here we have no problem, it's also 2 to the meter. But let's say, for example, label forcing and Miller forcing, I also have some of these things hold also there. Namely, what do I use? I use Z to the omega, so this group instead of omega to the omega. So a labor tree is now something in here, and translating it means bitwise in elements of set. So what it is? So do you think this is a sensible way of defining kind of translation invariant notion of labor tree? Maybe you have other suggestions what you could do as the group structure instead of Omega. Omega is not a group, I need some countable group to have something like that I can talk about LCO, that's labor null sets and so on. So even more, so this is at least one solution I would say where you can do something. And even more unclear to me is if I take Matthias forcing instead of labor forcing. This is, maybe you have any suggestion whether I can view the Matthias null set, so that a completely Ramsey, what is it called, Ramsey null, a completely Ramsey null set as a translation invariant notion somewhere. Because usually, you know, I like to view, for example, silver forcing, to view it as like silver trees on 2 to the omega. That you have like so uniform bit sequences, and then you have splitting. And so in Matthias forcing, you could also look at it this way, as a Matthias tree, so to speak. That this would mean that you have a very asymmetric situation because 0 and 1s do not play the same role with Matthias forcing. So it's in this usual sense, it's not translation invariant. You can just add an arbitrary real and get another Matthias tree in this sense. I'm not sure whether in some way it makes. So you could also take enumerating functions from Matthias forcing and view it somehow in omega to the omega, like increasing functions, but this does also not fit to, like, bijected to the group structure of sets. So I don't know. Whether there's some sensible way to do this. I guess this is all I wanted to say. I'm over time. Thank you very much.
Answers?
Well, the same, I suppose, is true, that you are available for any further discussion at the blackboards in the main building.
Sure.
Yes.
Yes. No, tomorrow.
Yeah.
I think you should decide.
So, think about
So it's fixed on, so you can fix
Yeah.
any, can you say?
I think so.
Yeah. Okay.
And then look at the conditions where you have pairs G tau, right? Where G is a countable function from 2 to the omega to 100 to 101, right?
Okay, so it's just
Just
closed
countable.
approximating.
And then you also have like promises where tau.
So this is for G. So the generic object is going to be G.
Yeah, so you go to G, but also you have these promises where, which is this tau is a countable set of, so it's a countable function that sends reals to countable ordinals. So which is the alpha that you promise that from that point on you will have this thing here, right? So this is what you're promising, right? For the t, this is what you want. For the t, there is some index, so from this point on, you will have
This
this.
is what I would like to have. So what is the tau? Say again, please.
The tau is this set of promises, right? It's a set of pairs t, comma alpha,
Oh, I see.
right? And then when you extend, you ask exactly that thing to happen.
Oh,
So you say,
like
right.
like a promise, like in Matthias voice.
Yeah,
Something
yeah,
that you
so-
say that from.
I think so. So I think
Okay.
so. You say for every beta which is above this point, right? Okay. If this guy is so that's f beta plus t is in the domain of G1 without G0, right?
Yes.
Then this thing should happen. So this should be
just
G1.
for all, for one, so for all new parts, or new, so what is for all new functions, or new, so this is the forcing, right? So this is the relation. So
So this extends
for
to-
stronger, you have also more of these promises.
Right, but I mean, when you look at the old promises, right, then you have to respect that. So
Yes.
it means for every t which is in, right, in the domain of t0, right, you look at t0 of t, that's a countable ordinal,
Yes.
and then you require that for every beta which is above that guy, right? If f beta plus t is in the domain of the g1, which is not in G0.
Which is like the next part, so to speak,
Yeah,
of the
if
generic.
it's new information,
Yes.
then this new information should satisfy this your requirement.
And so in the end, by density, so to speak, you have, whenever you have,
Right, so the forcing would be sigma close, so you're not having reals.
so CH stays the same,
And then I think the point is that f
But
is
you-
1 to 1, so you can, so given the condition by density, you have only fixed countable margin information. So given, let's say, so right, so given a t, right, the set of f betas, the set of these functions is, I mean, the function
so like pre-image, so
Yeah.
because it's injective, you cannot get too large pre-image, but just countable.
Right, so given a t, right, the set
Yes.
of the function sending beta to this thing is 1 to 1.
Yes,
Right, because
just,
because you said this is bitwise addition model.
yes, because actually, so we probably do not even need this very addition, but just any, this is just like a permutation of two trinity,
Right, right,
Uh,
something.
some projection,
Yeah.
which is important here, right? So it's
Yeah, yeah.
projection, so therefore, yes.
Right, so-
Okay.
Goes into so since this is 1 to 1, given any condition forcing, I can go to high enough alphas, which is so that right, so that the set of so that this set
This is not the
it's
exceptional part
it's not in the domain of function
of the
G0.
function, which would be problematic because we
Right.
have made the promises even
Yeah,
only
exactly,
afterwards.
Exactly.
And so,
So I can make a promise. I can
Yes.
promise now. I can go to this very high alpha so that I can extend.
yes, but so this is actually, this is just enforcing language now a proof under CH, or you
Right.
have really to force?
Yeah, I think so. Right? Because
So
this
it's
forcing-
actually just an inductive
Yeah.
construction.
Yeah,
If you
exactly.
put it so just in the forcing way, you
Yeah,
can
yeah,
nicely
yeah.
think about it. Right? Yes.
So it's sigma close, and you just have to meet out of one many dense sets, right? Because-
Yes, so this is so also for these kind of considerations, a long time ago I once thought about forcing, but then turned out to be seam closed because it's CH unit. So this is like you have the forcing axiom for one many
Sure,
sets.
sure,
This is what you could
Exactly.
put it.
Yeah,
so under CH.
Yeah.
Therefore, this,
So if I'm not wrong,
I will write it down
Okay.
myself.
Yeah.
So I'm sorry. I mean, I said that this was very expensive because I didn't think about it too much myself, but I just knew that this is exactly what I need by comparison with what I had in Saturday. But this would be very good. So then if this is true, then I guess, so then I have again checked the betas and the rest of the proof. It should work out that I can prove something with the only one, so to speak.
Cool.
So, yeah, so thanks a lot.